In this video, we're going to talk about something called harmonic motion. Some examples of harmonic motion is just things that keep repeating the same sort of motion over and over again. You can think of something on a spring bouncing up and down, pendulum going back and forth, Ferris wheels just rotating around and around. Anything that has that same repeated motion can be modeled using one of these harmonic motion functions. We're going to start with simple harmonic motion. And what we have for that, if the displacement d of an object at time t is given by d equals a times sine of omega t, or d equals a times cosine of omega t, then the object is said to have simple harmonic motion. And now we will define what all of the different variables are in here. We know d is the displacement. The amplitude of motion is going to be absolute value of a. The period is p equals 2 pi over omega. This is the time to complete one cycle. The frequency is the reciprocal of the period. So F is equal to 1 over the period, which is the same thing as omega over 2 pi. And this is the number of cycles per unit time. And just a note, we can also write these functions as d equals a times sine of 2 pi times our frequency times t, or d equals a cosine 2 pi frequency t. Those are the same formulas that we had with the omega in there, just rewritten a little bit different using the relationship of omega and the frequency. So let's do an example of simple harmonic motion. Let's suppose that a block at the end of a spring is originally pulled 6 inches below equilibrium. After release, the block makes one complete up and down cycle in 0.25 seconds. And we're going to answer a bunch of questions about this block. So what's going on here is picture a spring hanging vertically, and we have the block pulled down, stretching the spring out a little bit. And the block is 6 inches below equilibrium. Equilibrium would be where the block is sitting if we're not stretching or compressing the spring. So we pulled this block, and then if we release it, it bounces up and down, completing one cycle going up and back down in 0.25 seconds. The first question we're going to answer is, what is the period of motion? Now we just have to remember what a period means. That is the amount of time it takes to complete one full cycle. So it's going to be 0.25 seconds. Part B, what is the frequency of motion? Well, to answer that, you have to remember that frequency is equal to 1 over the period, when my period is 0.25 seconds. So my frequency is 1 over 0.25, which is equal to 4 cycles per second, and the units for cycles per second is hertz, HZ. Part C, what is the amplitude? Well, remember, the amplitude is the absolute value of the distance from equilibrium to the furthest point. So we had our block starting 6 inches stretched below equilibrium. So that would be -6, but that means my amplitude is absolute value of -6, which is 6 inches. Now part D, we're going to write a function to model this displacement. We write a function of the form D equals A times cosine of omega t to model the displacement D in inches as a function of time t in seconds after release. Well, let's just write down all of the things we know. Our A is -6 because we're starting -6 inches below, below the equilibrium. So it's negative because it's below, and 6 my amplitude. Now my period is given by 2 pi over omega, and we know that the period was 0.25. That means I can solve for omega to put it into this formula. Omega is going to be 2 pi divided by 0.25, which is 8 pi. So now putting all of that together, since I have D equals A cosine of omega t, I just fill in what I know. A is -6, omega is 8 pi, so I get -6 cosine of 8 pi times t. And then the last part of this problem, find the position of the block 6.25 seconds after release. Well, all I have to do for that is just plug in 6.25 into my displacement formula. So I get D equals -6 cosine of 50 pi. Now, cosine of 50 pi, we can actually figure out from our unit circle. Remember on the unit circle, over at this point, over here where cosine is 1, that's the even multiples of pi. And over here where it's -1, that's odd multiples of pi. 50 is even, so 50 pi lands right over there at the same spot as 2 pi. And that means cosine of 50 pi is 1. This means my displacement is just -6 inches, meaning that my block is again 6 inches below the equilibrium position after 6.25 seconds have passed. All right, let's do another example that's a little bit more complicated. We have a Ferris wheel, which is 120 feet in diameter. With its lowest point 3 feet off the ground. The wheel makes one full rotation counterclockwise in 1.25 minutes. Suppose 2 children are seated at the lowest point. Choose a coordinate system. With the origin at ground level, below the center of the wheel. And then we're going to answer a bunch of questions. The first question that we will be answering is we're going to write a model representing the children's horizontal position X in feet T minutes after the ride starts. So write a model representing the children's horizontal position X in feet at a time T minutes after the ride starts. So first, let's just draw a very rough sketch of what's going on. So here's my Ferris wheel. The children are located at the very bottom of the Ferris wheel, which we know is 3 feet above the ground. We're supposed to choose a coordinate system so that the origin's on the ground. And that means the position of the children to begin with is at 0, 3. The radius of this Ferris wheel is 60 feet. And our seat is initially at the point 0, 3. And my Ferris wheel is supposed to be going around counterclockwise, so going in this direction. That means that my x-coordinate of the seat is going to start by getting positive. It started here at 0, and it's going to get positive as the ride begins. So starting at 0 and then getting positive, that gives us a good indication that we should use the sine formula for the harmonic motion. So I know that my x position is going to be a times sine of 2 pi times my frequency times t. Now, my maximum deviation from our initial point is going to be an x equals 60, equal to our radius. Our x position is at the largest when we are one of these 2 points here, which is the full radius of the Ferris wheel. So I know that my A is equal to 60. Now, my period was 1.25 seconds, and that means that my frequency is 1 over the period, which is equal to 0.8. Now I have all of the info that I need. I can just fill in to what the simple harmonic motion formula looks like. X equals 60 sine of 2 pi times my 0.8 times t, which is 60 times sine of 1.6 pi t. And this models the horizontal position of the children t minutes after the ride begins. Now we're also going to model the height of the children, so the y position t minutes after the ride begins. So write a model describing the children's height, y, in feet above ground, t minutes after the ride starts. All right, so remember what the picture looked like to begin with. We had our Ferris wheel. My initial position was here at 0, 3, and my origin's down here on the ground, 0, 0. So initially, y is equal to 3. And it increases to a max height of the value of y at this point up the top. Now remember, the diameter of the Ferris wheel is 120 feet, but I'm also 3 feet above ground to begin with. So this max height is the diameter plus my initial, so 123 feet, halfway through the revolution. And so we are going to use y equals a cosine of 2 pi frequency times t with a vertical shift. And the vertical shift is given by the average of our lowest and tallest points, which is 63 feet. So let's find our amplitude. My amplitude is given by the difference between my maximum height and my minimum height over 2, which is 60. So my amplitude is 60, but since I'm originally starting below the equilibrium, it's going to be a negative 60. So we have A equals negative 60, since we're starting at the lowest point. This tells me that y is equal to my A, which is negative 60, cosine of 2 pi times my frequency, which is still 0.8, times t, but then I have my vertical shift of 63. So y is equal to negative 60 cosine of 1.6 pi t plus 63. Now part C, let's describe the children's position 2 minutes into the ride. Well, I know I can find the x-coordinate of the position and the y-coordinate of the position by plugging in 2 for t on both my x and y equations. But let's also think a little bit more deeply on this. 2 minutes, when I have 1.25 minutes for every single revolution, tells me that we've had 1.6 revolutions. This means the children have gone all the way around once and then gone another 0.6 of a revolution. So that's over half of a revolution. That means that if you think about, here's the Ferris wheel, they've gone around once and they've gone 0.6, so they're on the way back down the second time. So now let's just plug in to find our x and our y describing the children's position. So my x is equal to 60 times sine of 1.6 pi times 2. If I simplify that, I will get the x coordinate of the children's position. X is equal to 60 times sine of 3.2 pi, which is approximately negative 35.3. And I can get the y-coordinate of their position by plugging in to our equation for y. Y is negative 60 cosine of 1.6 pi times 2 plus 63. So y is negative 60 cosine of 3.2 pi plus 63, which is approximately 111.5. This means that the position of the children is at the coordinate negative 35.3, 111.5, and they're coming down the second time around. All right, so now we've had a couple examples of simple harmonic motion, but we also have something called damped harmonic motion. Now, damped harmonic motion is when the amplitude changes over time. So that's actually what happens quite a bit in the real world. If you think about it, we often have air resistance or friction, something that can be slowing down the oscillation of these objects. So if amplitude decreases with time, we say an object undergoes damped harmonic motion. So the displacement D of an object oscillating under damped harmonic motion at time t is given by D equals A times E to the negative CT cosine of omega t, or D equals AE to the negative CT sine of omega t for positive values of C, where A is equal to our initial displacement. So A is displacement at t equals 0. C is a constant called the damping factor. And your period P and frequency F are related by P equals 2 pi over omega, and omega equals 2 pi times frequency. So we're going to do an example using damped harmonic motion using some spring systems. So two spring mass systems have an initial displacement of 6 centimeters and oscillate at 0.25 hertz. The damping factors are 0.4 for spring 1 and 0.1 for spring 2. Write a function to model displacement for each system, T seconds after release. So what we can think about here is just think about stretching a spring. We have a displacement of 6 centimeters, and then the spring's going to be oscillating back and forth when we release it. We have an oscillation rate of 0.25 hertz. That's our frequency. So since I have my initial displacement as 6 centimeters, frequency is 0.25 hertz. My initial displacement A is 6 centimeters. We're going to choose the cosine model. Since I'm starting at a positive 6, and then it's going to start getting smaller initially. So we're going to have 2 different models, one for spring 1 and one for spring 2. But for both of them, we're going to use the model D equals AE to the negative CT cosine of omega t. Now, both of these have an initial displacement of 6. My first spring has a damping factor C equals 0.4, and my second spring has a damping factor C equals 0.1. Now, my omega, remember, is 2 pi times frequency. So that's 2 pi times 0.25, which is omega is 0.5 pi. And since my frequency was the same for both of these, my omega for spring 2 is also 0.5 pi. So all I have to do is fill this info in to the formula. So for spring 1, we're going to get D equals my A, which was 6, e to the negative CT, so negative 0.4 t, cosine of omega t. So cosine of 0.5 pi times t. And there is my function for the displacement of spring 1. For spring 2, I just fill in the info for spring 2. A is still 6. I have e to the negative 0.1 t because my c was 0.1 this time. And then I have cosine of my omega, 0.5 pi times t. And that's the displacement for spring 2. And that damping factor just changes how quickly the oscillation gets shorter and shorter. So how much the amplitude is decreasing over time. If you have a larger damping factor, the amplitude is going to decrease quicker than if you have a smaller damping factor. So that's all I have for you guys today. If you have any questions, feel free to drop them below. Or if you're a current student, you can also ask in class, office hours, or through email. And I'll see you guys next time.